And the last speaker of this morning is Professor Nazario Martín. He's a full professor of organic chemistry at the University Complutense in Madrid. He is also a member and vice director of India Nanoscience in Madrid. He has also many awards. And I would like also only to mention that he is the receptor also of the González Chimichan Prize, but now from the other side, from Italy.
Yeah, it was 3 years ago, but in 2 weeks I will be in Rome.
You are here thanks to her. You are the complement.
Yeah.
Okay.
Thank you so much.
And the title of the
is highly appreciated.
And the title of the talk is not that you have in the program. He's going to talk about other things. Okay, yeah. Nazario, go ahead.
So, as expected, someone said probably Nazario will say something about TTF. Nothing about TTF. I will tell about my title. Nothing about the title, because I asked to Eugenio and he told me there is no menu, so you can make your choice. So, but the lecture, I have it with me. So if you are interested, I can change, I can switch. Today, considering the audience and the participation of many physicists, the idea was to put something which could be of interest for everybody. It is 2 square. The other one was, yeah, okay. So I would like to mention about the search for hole transporting materials in perovskite solar cells. I know that there are in between the young people, there are at least 5 or 6 presentations, because there are some groups working on this topic. So that is because eventually I decided to move on this. So, well, from the starting of the Industrial Revolution over 2 centuries ago, progress has been intimately related with the use of fossil fuels, as you can see here. Here there are a variety of landmarks of the human being, but today I would like just to focus on this number. If everything is growing up at this rate, probably it is expected that in 30 years from now on, the population will increase to around 10,000 million inhabitants. So this is, if Mr. Putin agreed with this. So energy is for sure is one of the important problems facing mankind. And this is how to address this question. Well, of course that the renewable energies have to be considered. And among them, photovoltaics are probably one of the most promising alternatives. Probably most of you know some numbers about the sun, which is coming to the earth, but take attention to this, pay attention to this. If we were able to harvest 0.02% of the sun, of the energy of the sun coming to the earth, that would be more than enough to satisfy our needs. For 1 year. So that would be fantastic. However, the situation is not so good. We have to go to photovoltaic devices, and let's talk about efficiency, stability, and so on. So the first devices in mid-50s was nanocrystalline silicon. And in order to make shorter, there is the last generation solar cells could be considered first the all organic solar cells or plastic solar cell, the hybrid or grid cell or dye-sensitized solar cells, small organic molecules, and also the most recent perovskites. All these devices have something in common, which is the use of organic solvents, of organic materials. And organic materials can be used for these devices for different purposes, okay? So, and all of them are related with the fabrication of devices. So with this introduction, the menu for today would be just to show you very, very briefly some consideration about perovskites and hole transporting material, which is the topic of this presentation. The idea is to tell you what we carry out in the last few years with star-shaped molecules as hole transporting materials, And the main purpose for today, this would be some benzyl trithiophene, BTT, and other heteroatoms. But today I would like to focus on this heteroatom containing spiro-based HTMs, mostly those derived from phenoxacin and phenothiazines. What I want to show you today is that it is possible to get or to synthesize a whole transporting molecule which has the electronic features of the famous spiro, which is considered the universal HTM material, and also to see that it can be improved in terms of stability significantly. So the motivation is this one, just to make the design of whole transporting materials for a better understanding of the role of these compounds. So just very briefly for those which are not in the field, that this is the maximum record for silicon solar cells. The commercially available devices coming from silicon usually are around 16% efficiency because it's microcrystalline silicon. But this is dye sensitized or solar cells or grid cell solar cells, that this is the maximum efficiency when you are using a solid electrolyte. Organic solar cells, they jump it very recently from 18 to 21% or so, and the most recent perovskites, which has been certified over 25% efficiencies. In addition, if you consider the tandem solar cells constituted by silicon and perovskite, it is possible to go close to 30% efficiencies. I want to make a remark, which is this one, because some people claim that this perovskite have lead, and this is a nasty topic. But if you are looking for lead, please visit your cars, okay? That is lead by kilograms and so on. But look at this, silicon, usually the thickness of the active layer is roughly 200, 300 microns. But if you go to the perovskite, then you can find 200, 300, 400 nanometers. So we are talking about 3 orders of magnitude thickness. The thickness is lower than for silicon. This is an important aspect to be considered. So very briefly, these are the perovskites. They have many features, significant difference with other materials. Mostly, I would like to say that the charge carrier lifetime is very high, is over 100 nanoseconds. The long diffusion length, over microns, and the small exciton binding energy. That is so small that the exciton, the photon goes to the exciton, and the separation of holes and electrons occur very immediately. So originally, when talking about perovskites, what people consider how was operating, how work. This was the former idea. The photon forms the exciton, and the exciton has to go to the interface for separation. But that was wrong. That is typical for organic solar cells. What happened in the perovskites is that perovskite, the active layer, is a semiconductive material, and therefore, because of the small exciton barrier, the separation of the exciton occurs immediately, and holes and electron can move to the respective electrodes. So, of course, that this has to go through this electron transport layer and also hole transporting layer, which are critical for these devices. So this is what is going on in the perovskite. This is the typical architecture, the active layer, the perovskite, which is sandwiched by the hole transporting layer, electron transporting layer, and the 2 electrodes. One of them, of course, must be transparent in order to collect the energy, the sun energy. So, but what happened is that upon photoexcitation in the perovskite, the electrons can go to the titania, which is the electron transport layer here. At the same time, the holes are moving to the hole transporting materials. But then there are other expected but undesirable systems like charge recombinations and also all other kind of charge transfer processes, which I will not go into detail right now. These are the typical architecture of the perovskites devices, perovskite devices. Perhaps the most typical is the planar structure. This is what is called the NIP. N is a negative electron transport. This is the way in which the device is fabricated. So the negative, the negative or electron transport layer, the intrinsic, that is because the name I, which is intrinsic or undoped material, and the hole transporting layer, which is the positive or hole transport layer. This is the famous Spiro OMTAT, which is, I will tell you later on a little bit more about this molecule, which is considered as the best one. And the reason this happened with the PCBM in fluorine chemistry. I knew PCBM from the very beginning, and I never believed that the first molecule was synthesized was the best one all over the world. Impossible. Even by chance, it's impossible. And with the Spiro, the feeling is the same. So why is the best? Cannot be improved? Okay, that was the idea. So if you have the so-called inverted device, then you have to, the electrodes are moved. You know, now here the electrode is different, usually aluminum or silver. And okay, this is, we have also addressed this kind of cells, devices in collaboration with Juan Luis Delgado or Ivan Mora, for instance, just to give you a couple of papers on this one, because we develop fluorine chemistry as well. So let's go already to the hole transporting materials or layers. This is, if you need this layer here, this layer has to fulfill some optoelectronic properties. Among them is the HOMO energy level should be aligned with the valence band of the perovskite, as I will show you later on. Sufficient hole mobility, appropriate conductivity, high transmittance. This is in case of the inverted, because you need the transparent electrode. And then the right thickness. But also other chemical features are important to be considered. Good solubility, this is to prevent the formation of pinholes, and that is, this decreases the efficiency. Hydrophobicity, this is important because the whole transporting layer is not only for promoting the whole movement through this single layer to the electrode. It is also very important to protect from moisture and also oxygen. The perovskite, which is in this regard, is quite much more unstable, but also excellent thermal and photochemical stability, and to be inert, of course, with the adjacent layers, otherwise you are reacting. So, but this is important. Just to summarize, when the hole has to move from the perovskite to the electrode, it is therefore the whole transporting layer is blocking, is allowing the movement of the holes, but blocking the movement of the electrons, which must go in the other direction. And in addition, another very important issue is that remember to protect the perovskite layer against ambient regions. Okay, so this is the famous OMTAT. Here, this is the molecule. Molecule is a Spiro compound. It's a Spiro compound. This is the name for those that like, particularly for physicists. I know you are very much interested in the chemical names. So there are some advantages of this molecule. It's a wide band gap. It's a high HOMO level, which is important. It's minus 5.1 electron volts. It dissolves very well in organic solvents. This molecule is not planar, and it's a semi-crystalline. This is important with a glass transition at this value. This is important feature, but there are many drawbacks with this molecule. Which one? Low hole mobility. is an organic compound. Organic compounds are not characterized because they move charge very efficiently. So the mobility is 10 to minus 5. So, and also because of the low mobility, low conductivity. So, well, this is, in addition, because of the chemical structure, is a complicated synthetic protocol. And because of that, it is quite expensive material. If you go to Merck, it was around 500 euros per gram. Now, there are other companies that you can get it around 350 euros per gram. But in addition, you have to use it in a sublimation grade. So you have to sublime and you are losing material. So it's really very expensive, and therefore it's difficult to apply for fabrication for devices. That is because, well, if you want to use this molecule, in any case, you have to improve these values I showed you. So you need P-type dopants. But P-type dopants sometimes have some problems in terms of stability, but not what other people claim. So the best are no dopants at all, not necessarily. The question is to have dopants, but form quite stable devices, because in the presence of dopants, the efficiency of mobility and conductivity significantly increase and improves. So these are the typical dopants: terbutylpyridine, the lithium salt, and the cobalt-3 complexes. These are, in some way, they are oxidant systems, okay? I will not go very much into detail with this, just in case you have any question. So here you can see we carry out the revision of the topic a few years ago. In 2018, we published a Council Rep focusing on this was the title, Whole Transporting Materials. And you can find many different chemical structures. Most of them are by mimicking those of the spiro. You can see spiro systems here or different nature, okay? You can see that the efficiencies are quite good for the spiro in general. And also planar molecules, okay? This is a spiro as well, but this is a planar molecule. You have also donor and acceptor, quite simple molecules, by the way. And porphyrins can be also fine. So, well, there are many of them. Here are the most representative one, having very high efficiency, PCE values, photon to current energy conversion. So this, however, we have to say that despite the huge number of molecules, there is not a clear relationship in between the chemical structure and the photovoltaic performance. So now I will tell you very briefly in only a few slides, which has been our contribution. These are our papers with a couple of review, special, well, this one, this bulletin of the Chemical Society of Japan was a special issue in honor of Eiichi Nakamura. He was a very good friend, and this is one of the paper we contributed. Yeah, you can see here that we have mostly focused on the chalcogenides. I mean, oxygen, sulfur, particularly sulfur, that is because it's larger in size, and also selenium, just to test. And the star-shaped molecules are shown here. These are, well, I will go into details right now, but all of them have with a sulfur atom. This is 3, but here is the isomerism. We have played with this one. Is the same or not? Here, well, what you have here at the periphery are usually the paramethoxy diarylamines or paramethoxy, well, or 3-arylamines, as you can see here. This is the famous TPA, which is also widely used in these systems, but also some triacyltruxines. Antonio mentioned about truxine and acetruxines, which is a molecule very well known in his group for many years. So you can see that the number of sulfur is 3. 3 is also here, but it's not the same because here are isomeric structures. 2 sulfur atoms pointing at the same side is not the case like here, or you have we have increased the number of sulfur atoms, 4, 5, 6 atoms, sulfur atoms, and so on. We also use different heteroatoms, oxygen, selenium, and so on, and also some simple central cores as well. What is interesting to mention here is that the sulfur, the presence of sulfur in these molecules is very good because improve the charge delocalization and the intermolecular interaction. Now, you are right when you said about TTF. TTF eventually is appearing. We learn about the sulfur atom, but if you go to the famous book by Primo Levi, the periodic table, when you go to the sulfur chapter at the beginning, you can read, with sulfur, you never know. And this is for people who has been engaged in sulfur chemistry, this is absolutely right. Okay, so, but there is something which is interesting because in these molecules, because they are planar, you can consider pi-pi interactions in between them, but also sulfur-sulfur interaction, which is very efficient, by the way. But in addition, sulfur could interact with those components of perovskites, for instance, iodine or lead. And well, this is important. The second consideration is that all these molecules can be synthesized in gram amounts at very low cost. Actually, we carry out the study of this, and most of them could be, or many of them could be prepared around or lower than $50 per gram without considering the fabrication in big amounts. And the new molecules are good thermal stability, as I will show you with later on. So this is not our papers, but this is just a proof that the sulfur, these are whole transporting materials are coming from the same Chinese group, but this is with oxygen on the periphery, this is sulfur. This is sulfur, and what they determine by XPS, X-ray photoelectron spectroscopy, is that this is the perovskite alone, okay? And this is the perovskite together with the whole transporting layer has been deposited on the top. And you can see that there is a small shift of the orbitals of the lead, and the same happened with those orbitals of sulfur. So that means that eventually you are having an interaction in between the sulfur and lead atoms, okay? That is a very good indication for protecting and getting good results. So these are mostly most of the molecules we synthesize, but look at the energy alignment is pretty good and very good. This is the spiral as the reference, and you see that the HOMO level fits in all our molecules. This is gold. And this is the different perovskite, the monocation, the MAPI, the dications, and the state of the art with the trications perovskites. But the HOMO-LUMO level for perovskite are in agreement to be used with all these materials. So this is interesting to know about it. And just very briefly to say that, okay, the BTT, the benzo 3-thiophene, there are 7 in principle. You could expect 7 molecules, of course, with different properties. They are all of them in common. They are planar, strong pi-pi stacking interactions. But from this was the first molecule we started to work with. And we used the aryl amino as electron donor moieties, but also with this, with the carbazole unit having the TPAs, and this is the triphenylamine as well. So this is, we published this paper, and you can see here, this is the molecule we prepared. The efficiency was, this was come out a few years ago. At that time was really fantastic value, over 17%. But look at, just by modifying, by playing with the isomerism in the same molecule, the position of the sulfur is not innocent, because we consider that when you have 2 sulfur atoms pointing out at the same direction, you are improving the efficiency, because now you increase 1 point to over 18. but also here this is symmetric, but when you break the symmetry also has some importance. So we reach 19% efficiencies in this with these molecules. Another thing, of course, you should understand all these molecules were fully characterized and applied in the devices. Also, we played also with the modification of the heteroatom. This was with the sulfur, but we also use oxygen, nitrogen, and selenium. And well, in these cases, interesting results around surpassing 18%, most of them was reported. And now in the very last part of my presentation, I would like to focus specifically on this. You can see here the device we prepare in Madrid in our laboratory that you can see here. This is our laboratory at India Nanoscience. We were able to organize, at least from my knowledge, this could be the only laboratory preparing these devices on perovskites in our community. And well, there are many topics. While improving PC values, as I mentioned, over 25% has been reported, could be considered achieved, more or less. But there are other aspects like improving the long-term stability. This is over 1 year has already been achieved, but only in a very, very few cases. Today, I will show you another one. And perhaps the other idea is to improve the fabrication cost. Otherwise, you can prepare many molecules, but eventually will never be used for practical purposes. So these are the topics. Look at this. This is the surface area of devices. This has been made by Panasonic, okay, 30 by 30 centimeters, efficiency close similar to the silicon, okay? So in principle, this is a very good hint for future. So these are the molecules I would like to show you today, and this will be the last kind of molecules I will introduce you. And these are, you can see that here, the heterocycle with X oxygen, this is a phenoxazine, and when it's a sulfur, you have the phenothiazine compounds. And these are the solid we prepare. We prepare these new compounds in our group, was come out in solar last year. And let me tell you about it. Well, synthetically, it is important in contrast to what Antonio mentioned for the complexity, of course, that it is quite appealing for organic chemists. That I would say that is the main topic of the justifier our presence in the universe, you know, but but if you want to get something for practical purposes, complexity is a problem. So it is better to do it in a simple manner, a few synthetic steps, and with the highest yield as much as possible. So you can see from this commercially available phenoxazine or phenothiazine in 3 steps with relatively good yields without optimizing, you can see that, well, this reaction is, this is reaction with 2-bromo iodobenzene, and you get this compound, and replacement of the bromine by lithium in the presence of butyl lithium in THF at low temperature. You get here the lithium, and then the nucleophilic attack to the carbonyl group, and eventually you get a carbinol, and the carbinol, well, sorry, this is only for organic chemists, okay, but I finish immediately. An intermediate carbinol, which eventually react with the other benzene ring just to get the cycle. Once you have the cycle, another palladium catalyzed, it was mentioned by the powerful of these reactions by Antonio, cross-coupling carbon nitrogen. This is amination reaction, Buchwald-Hartwig reaction in the two reactions simultaneously, and you get a very nice compounds. Of course, I will not go into detail on the synthesis and characterization of these molecules. The mass spec confirm the presence of the molecules, and in a very, very pure state. Not necessary in these molecules to sublime to be used in the devices, okay? This is important issue. This was carried out by Enrique Ortiz, who is sitting down here, and he has been introducing everybody today. So these calculations reveal the spiro nature. Here you can see a sp3 carbon atom. What is remarkable is that in contrast to the spiro OMTAT, this is not planar anymore. You can see here with oxygen, and even this is larger angle with the largest sulfur atom. And also remarkable is this is a very weak interaction, but eventually you have an electronic interaction in between this ring, regardless of the oxygen or sulfur containing systems. So in principle, these molecules have something which is also another advantage on spiro. You have only TPA units, so only 2 triphenyl amino units, because this is one of the complex of the spiro. Spiro has 4, and because of that, many problems to obtain the pure material. Well, this is a very nice energy levels were calculated by Enrique. I will not go very much into detail, but you can see that this is the central core without the aryl amino units. And you see that, well, here is the same for the spiro, because spiro is the same one. So this is the orbitals for the HOMO. But when you have our molecular spiro with the phenoxacin or phenothiazine, you see that the HOMO now is localized on the heterocycle moiety, not here like in this. And this is the reason, this is the reason because the energy level is increased now here. The LUMO is basically the same and is located on the fluorine moiety. But just when you introduce the aryl amino groups, then the situation change in these compounds, simply because now the HOMO is mostly localized similarly to the spiro on the fluorine, but also in the electron donor units. So it's delocalized on the whole this moiety. And the LUMO is mostly maintained over there, more or less. But look at this, the band gap for our 2 new molecules are pretty much the same to that of the spiro. So this is one of the first things in common. This is the absorption and emission spectra for our 2 molecules in comparison with the spiro. And this is in the absorption spectra is, well, I could go much more into detail, but you can see this band corresponds to the electron donor moieties in the molecules, and this one corresponds to the heterocycle moieties. And the emission spectra is quite similar. You can see here the values is a little bit shifted in our molecules, but with this data you can find you can calculate the optical gap, and again here the first oxidation potential, which is good to determine the HOMO energy level, and also the LUMO are quite similar. Well, here is some optoelectronic properties. You can, well, sorry, these are the composition, the temperature, the composition, and the glass transition for this system. Well, the composition, the temperature is a little bit lower, but look at in our molecules, 400 degrees is much more than enough to be stable. But in the glass transition is a little bit higher. That means that in our case, we could consider that is mostly amorphous material, whereas in the spiro is a little bit crystalline together with amorphous. Here are some differences. Sorry, I made a mistake here. And now we go to the photovoltaic device, and you can see that we prepared the mesoporous configuration and the planar configuration. Mesoporous was carried out in EPFL in Switzerland, and the planar was carried out in Madrid. You can see here that the efficiency is pretty much the same. If we go to planar, spiro is over 18 for the spirometad, similarly. So the electronic is pretty much the same. But look at this. Here is, we start to see the difference. Well, the conductivity is in a Spiro is a little bit higher, it's around 3 times larger, but they are 10 to minus 4. And this is the quenching of the photoluminescence. This could be considered that the efficiency of the molecule to be able to move holes through the molecule. So they are quite similar as well, but this is, pay attention to this because this is the main difference, the main difference. So stability. In terms of stability, you see that, and now people say 30 days after, no. Now, in terms of stability, we carry out this study in over 300 days, almost 1 year, okay? And after 1 year, our molecules retain the 90% of the efficiency in dark. At this 30% humidity, okay? Look at this is the Spiro. Spiro is less than 50%. So this is a tremendous difference in between these. But if you keep your sample under illumination, after 1,200 hours up on illumination, our material still retain 94% efficiency. So this is for sure one of the best molecules considered so far as whole transporting layer. We carry out 17 devices in each of these studies. And you can see that in all cases, in blue, I put this in blue in order to remark that, in blue, the phenothiazine is surpass the properties of the Spiro in all cases, but it was only the field factor, which was pretty much the same, okay? So these are the conclusions. We have a wonderful material and surpassing here, as I mentioned before, those properties of the famous Spiro. And these are the very last molecule we have synthesized. Still, I cannot say much about these molecules, but we have carried out important modifications, introduction of heteroatoms, and so on. These molecules have already been synthesized in several hundred milligrams amounts, and you can see that the features are quite similar to the previous one. In some cases, are improving. So now we want to learn about the influence of these modifications, which are pretty much the same to that observed in the previous cases, hopefully with some of them improving performances. And again, just is the last slide, you can see that the HOMO and LUMO levels for the new molecules that you can see here exhibit a very good energy alignment as mentioned previously. So the conclusion is that we have a wonderful molecule, and it was presented last week in a Gordon conference on this topic. And well, not many, but some people was interested in determining how the molecule is interacting specifically with perovskite, maybe by using NMR crystallography, which is really fantastic. I like the name. So let me say that some of the people has been engaged. Here, this is not the last, okay, anyway. This is, we are carrying out this study with Agustín Molina, which is a Ramón and Cajal researcher, Inés García Benito, who is Atracción de Talento from Madrid community, and David Javier Urieta, who worked in his thesis and now as a postdoc is in our group. Collaboration with Nazario, as I mentioned before, and of course with my colleague and friend for many years, Enrique Ortiz, that we like to enjoy with science. And thank you to all of you for your kind attention. In any case, if we go 2 minutes late, the food will be there, so no problem.
sorry if I missed at some point, but the best material is evaporable, because at the very beginning you're thinking about solubility, but actually you want to be very stable. So something which is very insoluble but very easily to evaporate is the best material for this type of devices, or I'm wrong?
No, well, all these materials in particular, as they are spiral systems, they are not planar anymore. Because of that, they are quite soluble in organic solvents. They are in this audience. There are some people working with on perovskites, and they in the group of Unveiling, and they like to sublime the material. So the perovskite itself, and also this whole transporting layer can be sublime. And just by evaporation, actually it's not sublimation, but evaporation, they deposit the layer. In our case, as usually most of the systems, we do it by solution. So spin coating is the way in which you are preparing your devices. Okay, so from that viewpoint is for practical purposes, that for sure that the Unveiling has the possibility with big evaporators and so, but I would say that the best laboratory in Europe is in Valencia in this regard, evaporating these materials. Of course, there are others.
Any other question? Quick question? If not, question? No, well, the question is for you, we doesn't have the calculations. No, because if they think that
Eugenio, you have to ask to me, and then I will say Enrique can give you. Okay, so please follow the protocol.
No, okay. Then you see, you are calculating. Well, you have shown some HOMO-LUMO values, but these are calculated assuming that you have not solvents, not anything. But if you are doing that from solution, the calculations should change, and then, for example, the interaction you have put between the molecules will not be.
This is a very good point. It's a good point because, the reason is that always that you have the HTM alone, that is a calculation in the gas phase, or by using simulating also the solvent. But what is interesting is that, and you are right in this regard, is when you have it in contact with the perovskite, probably the interaction in between phases makes the difference, because probably the HOMO-LUMO levels can be modified a little bit according to this interaction. So that means that now is the question for Enrique. Next time, it is interesting to calculate not only at the molecular scale, but go to the interface and the interaction with the perovskite.
And the solvent.
But okay, yeah.
Okay, we have to stop here the discussion. Join me to thank all the speakers from this morning.